So today we will be discussing of the last two experiments of waves and oscillations. Okay. Then these are 14th and 15th experiments. Write down 14. 14. Write down. Write down the topic. Using a closed resonance tube. Using a closed resonance tube. Finding sound velocity and end correction, sound velocity and end correction. Right? So for this experiment, you need to know the wave patterns, standing wave patterns, longitudinal standing wave patterns caused inside a closed pipe, right? Caused inside a closed pipe. So both 14th and 15th experiments, we are going to find the same thing, right? Same thing means we are going to find velocity of sound, then end correction. For the 14th experiment, we will be using just a one fork, and by a direct calculation, we can find velocity of sound. It will be less accurate, right? Because we are not using a graphical method to find the sound velocity. But at the 15th experiment, we will be using a graphical method. So for that, we will be needing a set of tuning forks instead of just a one fork, right? Okay. Then this is the experimental setup. You can draw this with me. We need a tall jar, right? We need a tall jar. This is a glass jar, right? So then you have to immerse the pipe. So the diameter of this pipe is about 2.5 centimeters and the length is usually 50 centimeters, right? Those are just recommendations. This pipe, right? This is a hollow pipe. You have to put this into this, you fill this with water, then you immerse this. You have to immerse this this much, about this much, right? When you start the experiment, you almost immerse this tube inside the water. Then you slightly lift this pipe while keeping a vibrating tuning fork above this, right? Like this, right? It should be perpendicular. The prong should be perpendicular to this side, right? To the direction of waves. So this prong would send a wave through the pipe. Then what happens to the wave? This wave, sound wave, right? These are longitudinal waves. This would go into the pipe, then reflect off the water level. You know, that sound wave reflects off the water level, and that reflected and coming waves create a standing wave here. So the standing wave is like this. So this is the fundamental shape of that standing wave, right? Fundamental shape. So you know that there's an end correction. The wave does not stop here. It would slightly move above, right? Like this. So that is what we call end correction. This simply, that is the end correction. Then this length, we can say that is L1. So you keep lifting this till this occurs. So when this occurs, you would hear a sharp sound, right? Sharp sound means the pipe and the, I mean not the pipe, air inside the pipe and the tuning fork are in resonation, right? They are resonated. So they will have the highest amplitude and causing a standing wave pattern, which creates a very sharp sound, right? Then you can recognize there's this wave pattern here, right? So that is what you do usually. Then what do we do? Then, in order to find V and E, so those are two unknowns, V and E, right? V and E. In order to find V and E, you need another instant. So this is a one instant. You can build the equation using these. Then you have to go for the another instant. So to get that, you further lift, you have to further lift this tube. There's a stand connected to that, right? I haven't drawn that. There's a stand connected to that, right? Okay, you have to lift this further. Let's say you lift this up to like this much. Then the next wave pattern occurs here. So what is the next wave pattern? Could be like this. So this also has an end correction. And let's say you have lifted this up to L2. So you can notice that when you lift this pipe, water level here has dropped, right? Same pipe. So you know that when you lift this, the volume inside it decreases, so water level slightly drops. You have to notice that water level slightly drops. You have to do the same procedure. You are lifting this while having this vibrating tuning fork above it, like this, right? Okay. So in this experiment, you know that velocity of sound, right? This equation, gamma RT divided by capital M. So according to this equation, velocity of sound depends on temperature and the composition of air. This is molecular mass. This is average molecular mass of air, right? So it meaning composition of air. This velocity depends on both temperature and composition of air. So you can say sound velocity depends on what? One thing is temperature, another one is composition of air. So usually the composition is for dry air, composition is nitrogen and oxygen, right? When there are some water vapor inside, in that, there will be water as well there, right? There will be water as well. When there is, when you think about composition of air. So, for this capital T, right? Since this depends on capital T, so when you are pointing out velocity of air, you have to make sure that you mention the temperature as well. So when you are doing this experiment, you have to note down the room temperature, right? Temperature here. That becomes the room temperature. Usually the room temperature is about 25 centigrades. It could be any other value. You have to note it down as well, right? Another one is, so we are using water here, not something like a volatile, we are not using a volatile liquid. Like alcohol, we are not using that. Because the alcohol molecules could enter this and change the composition of air hugely. Water vapor also changes the composition, right? But that is less compared to other volatile liquids. So you have to make sure that you are using a less volatile liquid, right? Okay. Here, frequency of this one is known, right? So you have a known frequency, both are known frequencies, just a one tuning fork. So both are just a one tuning fork. Okay. Right. You can take these down as I am explaining. Now listen. So for this case, I can write this equation, right? So this part is a lambda over 4. This part is a lambda over 4, you know. I'm not going to explain the theories again, right? 1/4 of a standing wave. So this is lambda over 4. Lambda over 4 is equal to what? L1 plus E. L1, this length is L1. You have to add that. You have to add it, the end correction there. So L1 plus C. Then we can say lambda is equal to 4 times L1 plus E. Then I am going to apply V equals F lambda. So V is equal to what? F times lambda means 4 L1 plus E. So this is the equation for first case. So there are two unknowns, right? Frequency we know, L1 you can measure. L1 you can measure. What we don't know is end correction and sound velocity. So we are going to need two equations. That's why we got two instances, right? So this is a direct calculation. Then I'm applying that to here. So we have lambda over 4, lambda over 4, lambda over 4. So lambda over 4, 3 times 3. So that is equal to L2 plus E. Then you can say lambda is equal to 4 L2 plus E divided by 3. So we found a term for lambda. This lambda is constant for both, right? This lambda and this lambda same actually. Then for this case as well, just apply V equals F lambda. Then get V equals F is the same F, wavelength lambda, you can put this L2 plus E. So this is the second equation. So using these two equations, you can find V and E. So those are two simultaneous equations, right? You have only two unknowns. You can find V and E. So if you want to find velocity, you need to get rid of end correction from both, right? I'm not going to explain how to simplify this. Then if you need end correction, you can equal 1 and 2 equations, and then you can find the end correction. So using these two, you can find end correction and velocity. So this is a direct calculation, right? Not a graphical method. Direct calculation. We are not using a graphical method, it is a direct calculation. Okay, take this out and thumbs up once you've taken it down. Right. So take this down quickly. Write down main purpose of the experiment. Main purpose of the experiment is to find the sound velocity in air. Sound velocity depends on composition of air and temperature of air. Sound velocity depends on composition of air and temperature of air. Hence, a non-volatile liquid, a non-volatile liquid at room temperature, a non-volatile liquid at room temperature is used to fill the tall jar, to fill the tall jar. So that is the first point, right? Draw a line to this, right? Previous one, below that. Then write another point. Here, water is used. Here, the water is used. Concentration of water inside the pipe, concentration of water inside the pipe is slightly higher compared to air outside the pipe, Therefore, the experimental value of sound velocity, is slightly higher than the standard value. Okay. Now listen, right? So V equals gamma RT divided by capital M. So this is what velocity of sound, right? This equation gives us the velocity of sound. So here what happens, since there is water, the water vapor content here is higher. Concentration is higher compared to the outside, right? Outside air. So if it is higher here, what happens? This capital M, you may have heard that, right? Humidity inside the pipe is higher. So if humidity is higher, molecular mass, capital M, is less, right? This is what happens, right? You know that H2O is 18 grams per mole. Nitrogen and oxygen, they are 28 and 32. So these are heavy molecules compared to water vapor, right? Water molecules. So when there are water molecules here, concentration of water molecules is higher, what happens is capital M decreases. Average molecular mass here decreases because there's water molecules. The nitrogen and oxygen is replaced by water molecules, some of it, right? So the average molecular mass decreases when the humidity is higher. So now this decreases. So if this decreases, what happens? This is at the denominator, so the velocity of sound is slightly higher inside this. So it is a error in this experiment that we cannot prevent, right? Okay. If you use a liquid like alcohol, then that error would be more than that, right? Because alcohol concentration here, it is a volatile liquid, so it will totally change the composition of air there. Right. You can take this down. Okay, draw a line below that. Draw a line. Then in this experiment, we are using cotton, right? We are using cotton in order to apply to the bottom of this, bottom of the jar. We use cotton, right? The reason is, you know that when sound waves hits the water level, part of that sound wave gets reflected and another part gets refracted into, right? You know, you have studied reflection and refraction. So part gets reflected, which creates the standing wave pattern. That reflected part and incoming wave create this standing wave pattern. Then another part gets refracted, right? It goes towards the bottom and reflects off the bottom and comes back. And again here, those waves can mix with this standing wave pattern. This standing wave, creating a disrupting the wave pattern, right? So you wouldn't hear that sharp sound at the resonator. At the resonation, you wouldn't hear the sharp sound, right? So to prevent that, you need to stop these waves coming back. So you use a wave absorbent material to the bottom, right? So what happens when the wave comes through here, the sound waves, those would be absorbed by this cotton, right? Not totally, at least you can minimize that effect, right? So that's why you use cotton. You put cotton or any kind of like a rigiform, it doesn't matter, a wave absorbent material to the bottom, right? Okay. Draw a line, then below that write why use a wave absorbent material. Why use a wave absorbent material? Write that down. Write down sound waves, below that write sound waves are transferred by the tuning fork into the tube, tuning fork into the tube, creating the standing wave pattern. Part of that wave to the same line, right? Part of that wave gets refracted. Part of that wave gets refracted into the water, and it it is incident at the bottom. It is incident at the bottom. These incident waves, these incident waves reflects reflects from the bottom, reflects off the bottom, right? Reflects off the bottom and comes back full stop, right? And comes back. These reflected waves, these reflected waves can disrupt, can disrupt the incident wave, the standing wave can disrupt the standing wave inside the pipe. Standing wave inside the pipe. In this case, the sharp sound could not be heard, could not be heard or less sharp, or less sharp. To minimize this, to minimize this, a wave absorbent material, to minimize this, a wave absorbent material like cotton, wave absorbent material like cotton is applied, is applied to the bottom of the jar, to the bottom of the jar. Okay, another fact, right? Another fact. This is the first resonance, right? Now listen. This is the first resonance. This is the second resonance. So the energy is transferred at both cases are the equal amounts of energy, right? It is transferred by these tuning forks. Tuning fork. Here, a small air column is vibrated. The air column vibrated here is small here. But here you have a large air column. So at the same energy, but the air column to be vibrated is large at the second case. So what happens? In this case, the sharp sound you hear is less, right? At the second case. Understood? At the second case, it is less because you have to vibrate a large air column at the second case compared to the first one, right? So you have to notice that at the second resonance, as you are doing the experiment, the sharp sound is less, right? Okay. Write down. At the second resonance, at the second resonance, a larger air column, a larger air column is vibrated. A larger air column is vibrated. Compared to the first resonance. Compared to the first resonance. Therefore, the sharp sound heard at second resonance is less compared to the first resonance, right? Okay, so that is the 14th experiment, right? So we did that experiment using only one tuning fork. We used only one tuning fork for the 14th experiment. So the next one, it is 15.